So welcome back. So now in the previous chapter, we focus on how the current produce magnetic field and then how current carrying conductors interacting each other. In this chapter, we are going to look at the other way around, how magnetic field actually induces current in that sense. Okay, so this is the subject of induction, electromagnetic induction. So experimentally, it has been found that if you have a circuit like this where you have wires connect to a galvanometer. So which galvanometer is a ampere meter, but it's very sensitive to current, so it can measure very small current that is present in the circuit. Okay, so if you have setup like this and you approach your magnet to the loops formed by the wires, or you call it coils formed by the wires, then if there's movement in the magnet here, then you'll see there's non-zero current indicated on the galvanometer. So that means there's current actually induced by this guy. Okay, so you can approach the magnet to the coil and then pull it away from the coil. So then the current will be generate in opposite directions as the motions are different if it's approaching compared versus if we are pulling it away. Okay, and if it's stationary, the magnet is stationary, then there's no current produced in the coil. All right. Also, you can do a kind of a different version of this experiment. So you can have a circuit that has a primary coil, and so a coil is like you have different rounds of the wires wrapping and then stacking together. So in that case, if you turn on the switch over here, you'll see then there will be actually current induced in the secondary circuit here. Okay, and then if you open it, you'll see that again. But just shortly after this is closed, then this will actually return to zero. So there's no change in this coil here, because change in the coil or the current in the coil, it will produce a magnetic field. Now, different current produce different magnitudes of magnetic field. So the strength magnetic field strength is changing. So only when you have changing of magnetic field strength, then you'll have actually electric field generate here. So this is similar to what we have seen earlier. Okay, here. So if you're approaching the magnet to the coil, then the magnetic field in the coil gets stronger, as well as if you are pulling it away, then it becomes weaker in that sense. Okay, so if there's a changing in the magnetic field strength in the coil, then there's a current induced. Okay, so the conclusion is or a few conclusions here. So the first one is the current in the secondary coil is essentially zero as long as the current in the primary is not changing, and therefore the magnetic field in the iron bar is not changing. The current flows in the secondary circuit when the current in the primary is changing. It flows in opposite direction depending on whether the magnetic field is increasing or decreasing. So if it's increasing, the current goes in one direction. If it's decreasing, the current goes in the other direction. Okay. The magnitude of the induced current is proportional to the rate at which the magnetic field is changing. Okay, so you can have different rate of the changing of the magnitude of the current, so then the field will be changing accordingly. Okay, so basically, it depends on how much magnetic field strength you have through the coil. Okay, so you can imagine the coil being a kind of area. So if you have changing, so let's say you have a magnetic field going through this area. If the magnetic field is changing, so then the amount of current going through this area is changing. Okay, so this thing is something similar to definition of electric flux, right? So when we say how much electric field goes to a certain area, we call that amount to be the electric flux. So similarly, we call this as magnetic flux. So magnetic flux is a measure of how much magnetic field goes through a certain given area. Okay. So in this case, then we use again the same symbol phi, but we use the subscript m for magnetic field. So magnetic flux phi sub m equal to, then it becomes the how much magnetic field goes through the area, it's like in the electric flux cases, you do like E times the area, the vector, right? Dot product of the two vectors. So in this case, if you have just constant B field, then you'll be just doing B times area and then dot product. This is the unit vector in the normal direction of the area. So then that's a vector, okay? In the electric field, electric flux case, we do E dot N dot A. Okay, so in this case, it would be do B dot N dot A. Now, if your field is changing, then you'll actually divide it into small pieces. That means we are doing derivative of the area, right? So then you do the integration, kind of like sum over all of the small patches on the area, okay? So then B dot M in unit vector and then derivative of area, okay? So this is dot product. So the result will be BA cosine theta if it's a constant B field. Okay. If varying, you'll be doing integration there. Okay. So the angle theta is the angle the B field and the normal direction of this guy, the area makes. Okay. So that's the angle theta. All right. Now, oftentimes you have many turns of coils stacking together. So it depends on how many turns of coils you have. You'll multiply by the number of n. Okay. So the NBA cosine theta. Okay. Not the basketball association, but n is the number of turns. B is the magnetic field. A is the area, and then cosine theta. All right. So if there's a change in flux, then you actually have the current induced. Now, current is due to there's electric potential difference. Okay, if there's electric potential difference in the conductor, then there will be current in the wire or in the conductor. So then this is Faraday's law, which related to the current or the potential induced in the loop here, because this is a not the potential by battery, so it's an induced potential by the changing of the flux. So we call it induced EMF. Okay, so in this case, EMF induced here, but that's the same effect of creating current in the coil. Okay, it's equal to minus of derivative of phi m, the magnetic flux over dt, or if this would be changing constantly, and then you're doing the delta phi m over delta t. Okay, but with a negative sign. Okay, then we'll talk about the next segment later. And then if you have n turns of coil stacking together, then you'll be doing minus of n. So then the amount of the potential induced will be amplified by the number of turns. Okay. Let's take a look on the example first. This one says a single conducting loop of wire has an area of 7.2 times 10 to the minus 2 meters square and a resistance of 110 ohms. Perpendicular to the plane of the loop is a magnetic field strength of 0.88 Tesla. At what rate in Tesla per second must this field change if the induced current in the loop is to be 0.43 amps? Okay. All right, so let's take a look on this one. We'll first list the nodes we have, and then take a look on what we need to find. Okay, so the coil, maybe starting with is easier for us to sketch the problem. So let's say this is a circular kind of coil. Oh, it actually didn't say it's a circular, but that's assuming it's a circular. It doesn't say any kind of shape. Okay. So this is the B field that's perpendicular to the loop. Okay. So perpendicular to the loop, since this guy is initial, okay, 0.88 in this direction. So this loop has area of, so area A is equal to 7.2, 10 to the minus 2 meters square. It's only one single loop, so a number of the loop is 1. So it says the current induced I is equal to 0.43A. the resistance of the loop is 110 ohms. Okay. All right. So the Faraday's law says epsilon is equal to minus n derivative of the flux over dt, right? N is 1, so N is 1. You can calculate flux. So flux is equal to BA, right? And cosine of theta. Now, this is perpendicular to that. So the angle theta is 0. Cosine of 0 is 1. So just BA cosine of 0, which is 1. So BA. So then this is equal to epsilon equal to minus of derivative of B times A over dt. A will be a constant, but B is changing. Initially, B is 0.88, but B is changing. So that means this is minus A times derivative of B over dt. Okay. Derivative of B over dt, that's the rate the magnetic field is changing. So we are actually looking for this quantity. Okay, that's what we are looking for. A is given, so we just need to figure out this. All right. We are given I, we are given that. So then this can be calculated because according to Ohm's law, I times R should be equal to the potential, which is the induced EMF. Okay, so this is the induced EMF or potential. Okay. All right. So then you set it up that IR equals to minus A dB over dt, and you're looking for dB over dt. Okay. So this gives you dB over dt equals to IR over A, and there's a minus sign. Okay. So you go plug in the numbers, I 0.43 amps times R 110, and then over A 7.2 10 to the minus 2 meters squared. That gives you just minus 6.6 times 10 to the second Tesla per second. Okay. And you are looking for the rate, at what rate is changing. So you don't care about the actually the positive and minus sign. Okay. So that's the rate of the changing. Because the rate of changing is talking about the magnitude. Okay. Okay. Let's go back to the slide. All right. So now let's take a look on the minus sign on Faraday's law, like the induced EMF equal to minus n derivative phi over dt. Okay. So the minus sign comes from Lenz's law, which says this is what Lenz's law says: an induced current always flows in a direction that is opposed the change that caused it. Okay. So what does that mean? So if let's take a look at this example, okay? So let's say you have this coil here, okay? Now you have this magnet approaching it, right? So when you're approaching it, the magnetic field in this coil gets stronger, right? Because you're getting closer to it, right? So then you have increasing magnetic flux here, okay? So that's the change in the coil, all right? Now, there's a change in magnetic flux there, so there will be induced EMF in this coil, and as a result, there will be a current. We can call it an induced current in a coil, okay? So the induced current will oppose to the change that caused it. So as you are approaching it, you have this current induced, right? So then this current, the effect of this current will actually oppose to the change. So the change is due to the increasing in the flux. So then the current here will result in, because there's current in the conductor, then it results in the magnetic field. So the magnetic field by a current in the coil, we can use the right-hand rule, or the thumb goes in the direction of the current, the induced current. So the magnetic field then goes in that direction. Okay. So the induced magnetic field then by the induced, or the magnetic field produced by the induced current, then you can see it's actually opposite to the original, the magnetic field of the original magnet, right? So that's what it means. So this magnetic field produced by the induced field is opposite to the increase, okay? Now, on the other hand, in scenario B, if you pull this magnet away from the coil, okay, then the flux in the coil decreases. So there's a change of the flux in the coil. So then there's an induced current in the coil. All right. So then because your flux is decreasing, so the field, magnetic field produced by the induced current should then compensate the decrease of that. So that means the magnetic field produced by this induced field will be then in the same direction as your external magnet. Okay, so then because as you pull it away, the magnetic flux is decreasing. So then to oppose that decrease, the induced magnetic field is in the same direction as the external one. Okay. So those are two scenarios, okay, of Lenz's law. So as a result, because it's opposed to the change causes, so then in the Faraday's law, you have the negative sign, epsilon equal to minus of derivative of phi over dt, okay? All right, let's take a look on this circuit over here. So if you have a circuit over here, like there's a light bulb in the circuit, you have this rod that is moving. Now there's a magnetic field in the region that is pointing out of the paper towards you, right? So as you make this guy move, the rod is moving. So then in this closed circuit, we can consider this kind of like a coil closed circuit, right? So the B field is not changing, but in this case, actually the area is changing as this guy moves down, right? So then overall B times A is decreasing. So flux phi equal to B times A is decreasing. So in that case, the flux is changing. So then there will be induced actually EMF in the circuit and then on this rod, okay? So a current will be induced in the circuit. So then the light bulb will light up, okay? Similarly, if you pull the rod away, then there will be, or in this case, so what we have is because there's a induced magnetic field here, or induced current here in the circuit, the induced EMF there result in the induced current. So then as your rod is going down, right? So it's decreasing, the flux is decreasing. So in order to oppose that cause, that change, then the magnetic field produced by current should be in the same direction of the B field inside the coil, right? So then to slow down the decrease of the magnetic flux. All right, so then the current will be going in that direction because the magnetic field has to be in the same direction as the original magnetic field, right? So then in that case, so the current in the rod should be in that direction. Now, if there's a current in the rod, there's an external magnetic field, so then there will be a magnetic force on that guy, which is in that direction, which is slowing down the motion of this guy towards the lower end so then the magnetic force, this is the magnetic force. You can use the right-hand rule. So your thumb goes in the direction of the current, your forefinger goes in the direction of the B field. So your palm is facing in the direction for the magnetic force, okay, on that guy. All right, example here. So this one says, as shown in this figure, a circuit has an area of 0.060 meter square, contains a R equal to 1.0 and ohms, and then resistor, and then a C equal to 250 microfarad and charged capacitor pointing into the plane of the circuit is a uniform magnetic field of 25 Tesla in 0.010 second, the magnetic field reverses direction at a constant rate to become 0.25 T pointing out of the plane. What's the maximum charge accumulate on this guy? Okay. So let's think about this guy. So if this is then a closed circuit here, this will be the area. It tells the area of that circuit. Now the magnetic field is changing. So then the flux through this circuit, the surface of the circuit is changing. Okay. So then there will be induced EMF in the circuit. So that means it's like you adding a battery somewhere, okay, in the circuit. So then this will become an RC circuit, right? Now the EMF for the circuit or the potential for the circuit should be the induced EMF, okay? So we can calculate for the EMF and then we can calculate what will be then the charge on this guy, okay? So the area is given as 0.060 meters square. This is equal to minus d phi over dt. And this is minus dBA, right? Phi equal to B times A over dt. So then minus dB over dt times A. So it tells you this one, and it kind of tells you this because it tells you time delta t and how much change will be the magnitude. It changes direction, right? From say positive to minus. So positive 0.25 to minus 0.25. So then this is like minus delta B. You can do delta B over delta T because gives you the time. Epsilon equal to that. So minus of dB will be from minus 0.25. That's the final minus the initial. And then divide by 0.01 second. And then times the area, 0.060 meters square. Okay. So that gives you 3.0. 3.0 volts. So that's your EMF. All right, we're looking for charge. So for the charge, so we can assume that this guy is, so during the process, the 0.010 second. So this guy, that's assuming it's fully charged, right? So then how much charge would that be? So Q, assuming fully charged, Q then will be equal to C times V, where V will be equal to epsilon, right? So Q equal to C times epsilon. So then, C is 250 10 to the minus 6, and this guy is 3. So that gives you 750 times 10 to the minus 6 coulombs, or you can say 0.750 millicoulombs. Okay, so all 7.5 times 10 to the minus 4 coulombs. Okay. Now let's check our assumption. We are assuming it's fully charged, right? So that means this has to be like at least, as we say, if we learn in RC circuit, for a capacitor to be fully charged, the time is about like 5 times of the time constant, right? So let's see if delta T is actually greater than 5 times of the tau, where tau is equal to R times C, so 5 times of that. So if that's true, okay? 5 times R, given here R is 1, and C is 250 times 10 to the minus 6 farad. So this gives us 1.250 times 10 to the minus 6 farad, which is 0.00125 1, 2, 3, 4, 5, 6. Yeah. second. Okay, so which delta t that is 0.01 second that is greater than that. Okay, so that's true. 0.01 second is greater than, it's about 8 times of that. So that's fine. So we are fully charged. So yes. Okay, so then that's right. So if not, then you'll do q as a, or you can do q as a time function t, like c epsilon, and this is for the charge is 1 minus e to the minus t over tau. You can calculate it that way. Okay. All right, and then if you calculate it that way, it should be pretty much also close to that guy. Okay, so this will be another way, okay, of doing it. All right, let's go back to the slide. So then let's take a look closer look at this the circuit being powered by the movement of the conductor here. Okay, so when you have this guy, now this time let's look at the other way around. So the conductor is moving in this direction, and then it actually increases the area of the circuit. So then the flux through the circuit increases. Okay, so in order to oppose that change, then the induced current here will produce a magnetic field that is in the opposite direction of the initial. Okay, so then B field will be going inward, so then the current will go down. Okay, so this is what you would have. So you are moving this guy to the right, that means you exert external force on that, but then at this time, because there's an induced current, there will be a magnetic force that will be opposed to the external force, right? So as you increase more, as you go this guy, so assuming this force is a constant force, right? So then V will be increasing, then this guy will be also increasing, this will be increasing, current will be increasing, but at one point, then this guy will be equal to that. So this will be canceling out. Then you'll have constant velocity going through, okay? So at equilibrium, you'll have these two equal to each other, and then the velocity will be constant. So that's analyzed. Then when it reaches constant, the flux will be still be changing. So then equal to the constant magnetic field times the changing area. The changing area will be equal to, so it's area, right? So it will be equal to the width times the amount of the distance traveled by the rod, right? So that case. So L will be the width, and then the distance traveled will be V times delta T. So that will be then the area, okay? So that's delta phi. Now in this case, we only have one loop here. So this is equal to 1. So the induced EMF then inside the circuit will be delta phi over delta T. So delta T and will cancel out. At the end, you'll just have B times V times L. Okay, so the width of the rod and then the B field, the V. Okay, so if you have a rod that is moving along the inside the magnetic field, and that rod is perpendicular to the magnetic field. So it generated the induced EMF of magnitude of BVL. Okay, then it's like this rod. Now you can treat it as like because it produced the motion of this rod produced the induced EMF, and that could be just equivalent to a battery. Okay, so and there will be, in that case, there will be like a potential difference across the two ends of the rod, which then produce an electric field there. So the electric field then will be equal to, you can do the induced EMF divided by the width of the rod, okay? Then BVL divided by L. So then E inside the rod is equal to B times V. And the force on the rod, the magnetic force on the rod, okay, will be equal to I times L times B. The current I will be equal to the induced EMF divided by the resistance, okay, and times L times B. So that will become B squared VL squared over R, okay, so that's the force. And this force will be equal to the pulling force. All right. So then as you are pulling the rod with the velocity of V, so that's the mechanical power you exert on the rod. So mechanical power should be equal to F, the driving force, right? The pulling force is kind of driving force times the V. So F equal to magnetic force, which is VL square, B square VL square over R times V. So then it's B square V square L square over R. You have current in the rod in the circuit, and then you can use that to calculate the electrical power of the circuit, which is I squared times R. I will be BVL over R times R. So then you'll square the B square V square L, but you have R square in the denominator multiplied by R, then you only have R remain. Okay, so then it becomes, again, B square V square L square over R. So you can look at these two, they are the same. So your mechanical input, right, becomes your electrical output. They are equal to each other. All right. So you are converting your mechanical power into your electrical power. Okay. So that's how power is generated. Electrical power is generated. Let's take a look on this example. So this one says in the figure showing here, in the figure showing here, a zero resistance rod. So this rod has zero resistance. Okay, so all the resistance from the circuit is coming from this resistor. The rod is sliding to the right on the rail here, and with zero resistance. And so the first zero resistance refers to the electrical resistance of the rod. The second zero resistance refer to the rail has no friction. Okay, so if you're wondering, this rod is on the rail is separated by 0.500 meters. The rails are connected by this 10 ohms resistor, and the entire system is in the uniform electric field of 0.750 Tesla. Find the speed at which the bar must be moved to produce a current of 0.175 in the resistor. Okay, so the motion of the rod is going to cause the induced EMF. Okay, so then that EMF will be the power supply of the whole circuit. Okay, so we are looking for V, and we are given that L, in this case 0.500 meters. We are given B equal to 0.750 T. We are given current I equal to 0.175 A. We are given R equal to 10 ohms. All right. So in this case, IR, right? So I think we can calculate, given I and R, we can calculate induced EMF. Induced EMF will be equal to I times R. Okay. And then induced EMF can also be expressed as B times L times V. Okay. If you go a couple slides back, that's what you will see. So B times L times V. So then you're set up this way. So this guy equal to that, and you are looking for V. So I R equal to BLV. So V equal to IR over BL. Okay. You'll just plug in numbers. 0.175 amps times 10 ohms over 0.750 Tesla times 0.500 meters. You get 4.67 meters per second as the speed. Okay. All right. And I think I just realized one thing. In the previous example, I think I forgot to mention about in the example we check here, it also wants to find the sign of the charge on the upper plate. Okay, so we have to determine then what will be the direction of the current. So then we can see if this is a negative charge generated on the upper plate or positive charge on the upper plate. Okay, so in this case, the magnitude, so the B field is going into there. Okay, the magnitude of B field actually reverse direction. So that means it decreases, right? So to oppose that change of decrease in magnitude, then the current, induced current should have a magnetic field produced that is in the same direction of the original B field. Now inside the circuit, okay, we just have to worry about the magnetic field inside the circuit. Outside the circuit, you don't have to worry, okay? So inside the circuit, so it goes in. So that's how the B field should be going in. If you look at the bottom bottom wire on the top wire, then you go that way, right? You curl your forefinger in that way, so the direction of the thumb. So then the current is actually in the clockwise direction. You'll get actually positive charge on the upper plate here. Okay, so there the charge will be positive. Okay, so the sign of the charge will be positive on that one. All right. So we'll stop here for today, and then we'll come back next time for the reminder of the sections in this chapter. So I'll see you another time. Bye.